Hello, here we are working out another moment of inertia, this time for a uniform disc, a uniform circular disc. So, and it'll be rotating about the center again. So here it is sort of side on. So we can have this central axis of rotation. As we know with these things, actually I'll write down the formula first of all of what we're trying to do. So we're summing up all of the individual bits if we're dividing the disc into n bits. And we're adding up the mr squared for each one of those is going to give us the moment of inertia. So as always, the question is, how are we going to divide up this disk? Right, well, let's go for sort of concentric rings about the center. That'll be fine. So if we take each one of these rings, so here's a little ring that I'm trying to sketch in, and you think we can have loads of these extending, you know, all the way out from the center, all these concentric rings going on. We'll have that the mass of the whole disk is our capital M, the radius of the disk is capital R. This is all fairly standard stuff if you've been looking at the previous videos. So what's going on for our ring then? What's happening here? We can say that the width of this ring is dr, and the radius of the ring is lowercase r. So how are we going to work out what the mass of this ring is? Well, we know that the area, so the area of this ring is going to be 2 pi r, so that's our inner circumference of the ring, multiplied by dr. Then we've got to divide it by the total area of the disk, which is pi capital R squared. So that's the fraction of the area of this disk, and it's a uniform disk. So if we multiply that by m, we're getting little m. That's the mass of our little ring that we've got there. It's the area of the ring divided by the area of the disk multiplied by capital M. So the fraction of the disk multiplied by capital M. Right, so this is all going to be fine now. We can just pop this into our formula here. I'll just move the equal sign over the side a little bit. We're going to be integrating from 0 to r because, yeah, the rings are just moving from 0 radius out to r. You know, we're not going from minus r to plus r because we have to look at what the radius of the ring is doing. And the radius of the ring is going from 0 when we're right in the middle up to capital R on the outside. So that's the limits of our integration. Then we put in our mi, which is 2 pi r dr over pi r squared multiplied by m, and then we've got our r squared at the end. So we've got a few things we can cancel off of here, or well, we can cancel the pi's. Looks as though it's around about it. So what is our integral we're actually doing here? Let's take our m and the 2 and the capital R squared onto the outside. Integrate from 0 to r. What are we actually left with? R cubed dr. So we've got 2m over r squared. That's going to r to the power of 4 over 4 from 0 to r. The 0 is going to leave us with nothing, so we've just got r to the power 4 over 4, and then we're dividing off this r squared, and we've got a factor of 2 in all of this. So all in all, in the end, that's going to leave us with the m, a capital R squared, and a 2 on the bottom. So yeah, same old thing, it's just a different way. We've now had 3 different ways of dividing up these shapes. We had the rod where we were going lengthways, we had the ring where we were dividing up around the circumference, and now we've got the disc where we're taking rings moving out from the center. So we've got 3 different ways of dividing up, and then once we put that into our integral, it's all dead easy then, fairly straightforward calculus.